The new orbitals formed are called hybrid orbitals. After intermixing of orbitals, the new orbitals will form, that will called as hybrid orbitals. Due to SP2 hybridization, BF3 molecule has trigonal planar structure. It is having triangular trigonal planar structure will form. Bond angle is, all the bond angle are equal to 90. That's why all the bonds are equal in length. All the side it is having 90 degrees. Hello everyone, this is Harshita Bhavasar from Vidhyaashram PU College, Temple of Excellence. Today we are starting up session 4 from the chapter Chemical Bonding and Molecular Structure. In the last class, we have discussed about geometry of covalent molecules, VSEPR theory, that is valence shell electron pair repulsion theory, and valence bond theory. These are the content, or these are the topics we have discussed in the previous session. Based on these topics, here we are understanding about the types of orbitals. Now we will see the next topic by understanding that previous one, that is hybridization. In that hybridization, SP3, SP2 and hybridization involving sp and d orbital also we'll see today, and another one, coordinate bond. First, we have to understand what is hybridization. We know the types of orbitals. So, if that types of orbitals get intermixing, the hybrid new orbitals will form with a comparable energies will be present, right? So, that the intermixing of orbitals to form a new hybrid orbital, we'll call it as hybridization. We'll see now. The intermixing of atomic orbitals of the same atom having comparable energies to form an equal number of identical orbitals with same energy and shape is called hybridization. The intermixing of atomic orbitals means in the same atom it should be present. If it is carbon means 1s2, 2s2, 2p2 we will write. That different atomic orbitals present in same atom should get intermixed with having comparable energies, and why it will form? To form, or why, what is the purpose of forming means to bring that orbitals in the as identical orbitals with equal energy and shape. That is called hybridization. The new orbitals formed are called hybrid orbitals. After intermixing of orbitals, the new orbitals will form, that will called as hybrid orbitals. Hybrid orbitals are distributed in space around the nucleus as far away as possible to minimize the repulsion between the electrons in them. We know all the electrons are negatively charged species. So, if electron is present little bit near to each other, it will form or it will create some of the repulsion. So, the hybrid orbitals are distributed in space around the nucleus as far as possible because it should not get repelled by one another. Depending on the number, nature of orbitals involved, different types of hybridization are possible. Depending upon the number of orbitals, depending upon the nature of orbitals, the new hybrid orbitals or the types of hybridization will be possible. The shape of molecule can be predicted by type of hybridization involved. What is the purpose of doing hybridization and all the kinds of hybridization means? To predict the shape of a molecule. How we can predict the shape of a molecule accurately? It can be predicted by based on the type of hybridization. These are the major points to understand in the hybridization concept. First one, we'll see SP3 hybridization. That is one kind of hybridization. Mixing of 1s orbital and 3p orbitals of an atom to form 4 identical orbitals is called SP3 hybridization. SP3 means 1s, 3p orbitals should be present. The new orbitals formed are called SP3 hybrid orbitals. They are directed in space towards the 4 corners of a regular tetrahedron, making an angle of 109 degree 28 minutes. Means after this 4 new hybrid orbitals will form, it will form in a shape or a geometry called regular tetrahedron geometry. It is having a bond angle of 109 degree 28 minutes. In the bond parameters itself, we have understood that bond angle will be determined by based on the geometry, right? When it will be distorted, when the presence of lone pairs present, it will be distorted. So, we'll see now. For example, methane. This is the molecular formula. Now, we have to understand the overall geometry here. First carbon atomic number is 6. What is the general electronic configuration? 1s2, 2s2, 2p2. In 2p, that is p, px, py, pz is present. That's why here distribution of electrons has been made. In the excited state, this s orbital also will get separated and it will be present in 2pz orbital. So undergo SP3 hybridization, S1 P3. See here, hybridization, 4 SP3 hybrid orbitals are present. 1 2 orbital and 3 2p orbitals combine to form 4 SP3 hybrid orbitals which are oriented towards the corners of a tetrahedron. Each SP3 hybrid orbital has 1 electron. These hybrid orbitals overlap with 1s orbitals of 4 hydrogen atoms, correct. What it will do? 4 individual or 4 single electrons will get overlap with 1s orbital of 4 hydrogen atoms. Okay, here 1 2s orbital, this is 3 2p orbitals. How it will form? The 4, it will be tetrahedron. See here. Tetrahedron form will be present. See SP3 hybrid orbitals, this 4 atoms of hydrogen will get linked like this. This is 109 degree 28 minutes. This is methane molecule. Okay, overall how it will form. Due to SP3 hybridization, methane molecule has tetrahedral structure with 109 degree 28 minutes. This is how the hybridization will be discussed. Another one you can see here, ammonia, NH3, nitrogen, overall 5 valency is there. This is 1 lone pair of electron. Usually it should form a regular tetrahedron form itself, but due to this lone pair of electrons are present, that repulsion will take place. Due to that lone pair of electrons, it will form trigonal planar. It will form. Otherwise, it should form tetrahedron structure, but it is having SP3 hybridization only. Due to this lone pair of electrons present, it will form trigonal pyramidal structure. Okay. Next one, SP2 hybridization, mixing of 1s orbital and 2p orbitals of an atom to form 3 identical SP2 hybrid orbitals is called SP2 hybridization. All the 3 hybrid orbitals are in the same plane and are directed towards the 3 corners of an equilateral triangle with the bond angle 120 degree. The unhybridized pz orbital lies perpendicular to the plane of SP2 hybrid orbitals. What is the example? BF3. We have to see the electronic configuration of boron, that is 5, 1s2, 2s2, 2px1. Right. In the excited state, this S will move to here 1 electron. That's why it will move to 2py1. S1, P2, SP2 hybrid orbitals will form. PZ orbital is perpendicular to the plane of SP2 hybrid orbitals. These hybrid orbitals to form 3 BF sigma bonds by overlapping with 2p orbitals of 3f atoms. See here, one is B here, 3f. F is having 7, within that 1 lone pair will be there, no? 1 single will be formed here. It will form like this. This is BF3 molecule having 120 degree. Due to SP2 hybridization, BF3 molecule has trigonal planar structure. It is having triangular trigonal planar structure will form. Next one, SP hybridization, mixing of 1s orbital and 1p orbital of an atom to form 2 sp hybrid orbitals is called SP hybridization. The 2 sp hybrid orbitals are directed linearly with an angle of 180 degree. Hence, the molecule with sp hybridization will have a linear structure. It is having 180 degree, okay, no that much repulsion is present, so it will form linear structure. The other two hybridized p orbitals lie mutually perpendicular to each other. It is having p orbitals in mutually perpendicular. That's why it will form linear structure. For example, BeCl2. In BeCl2, central atom is beryllium, that is atomic number is 4, 1s2, 2s2. It has 2 electrons in the valence shell. See here, 2 electrons in the valence shell. 2 sp hybrid orbitals. Means it will, in the excited state, it will jump here. See here. Only S1, P1. Px, Py are mutually perpendicular. So, linear in structure. One of the 2s orbital electron is shifted to the vacant 2px orbital. The half-filled 2s and 2px orbital mix together to give sp hybrid orbitals containing 1 electron in each. The half-filled 3pz orbital of the 2 chlorine atoms overlap with the sp orbitals to form BeCl sigma bonds. How it has been formed here, see. Here the intermixing is taking place, but it is having linear structure. See, it is 180 degree of bond angle is present. That is how we have to understand the concept of hybridization. By understanding the hybridization concept accurately or more to the accurate level, we can understand the geometry of each and every molecule. Here bond angle is also very much important. Next, hybridization involving 3 orbitals, that is sp and d orbitals. Elements of third period having vacant d orbitals. Third period means like this we have to see. Okay. The 3d orbitals have energy comparable with orbitals of both third as well as of fourth shell. Hence, the d orbitals are involving in the hybridization with the s and p orbitals of either the third or fourth shell in forming polyatomic molecules like PCl5, SF5 and IF7. Hence, the d orbitals are involved in the hybridization. The s and p and the third and fourth shell forming polyatomic. Poly means many atomic shells will be present here. See here, in that SP3 dehybridization means overlapping of 1s, 3p and 1d orbital to give 5 sp3 dehybridized orbitals will form. And 3 hybridized form towards the corner of the equilateral triangle and are called equatorial orbitals. Remaining 2 hybrid orbitals are perpendicular to that equatorial or triangular plane, one of the plane and the other below the plane. One will be the above the plane, one will be the below the plane. In between 3 hybrid orbitals will be present. These 2 orbitals called axial orbitals. The bond angle between the axial orbitals is 120 degree and the angle formed by the equatorial orbitals with axial orbitals called 90 degree. Equatorial means this is axial. This is 90 degree. This is 120 degree. See here, example PCl5. Phosphorus is having 15 atomic number, that is in the ground state 1s2, 2s2, 2p6, 3s2, 3px1, 3py1, 3pz1. Overall 15. In the excited state, this will jump to here. In the 5sp3, 5 means because S1 will be present, here it will jump, right? S1 will be present, P3 and D. It has already jumped here, okay? See here the overall intermixing. C5 is present, 1, 2, 3, 4 and 5. All the p orbitals is mixing here and they have told 3 trigonal, that is equatorial plane is present, above one line and below one perpendicular to each other. That is axial angles and these are all equatorial angle, okay? For this equatorial, 2 perpendicular p orbitals are present, that is here, see here, Cl and Cl. This is perpendicular, but this is equatorial angle. This is 90 degree, this is 120 degree. Next one, in this here only, shape trigonal bipyramidal will form. Axial angle is 90 degree, equatorial angle is 120 degree. Axial bond length is more than equatorial bond length. There are 2 axial bonds and 3 equatorial bonds. Axial bond pair of electrons experience relatively larger repulsive interaction. Hence, axial bonds are longer than the equatorial bonds. This is axial bonds. It is having more repulsive interaction than this equatorial bonds. That's why it is lengthwise it is more than the equatorial bond length. Next one, SP3 D2 hybridization. For this example, SF6. Before that, one SP3 and 2 d orbitals will be present to form hybrid orbitals. For example, SF6, for sulfur 16 is the atomic number. For neon is completely 10, right? After that, 3s2 and 3p6. In the excited state, here 3s1, 3p and 2 will jump here, 3d. SP3 D2 hybridization will takes place. In SF6, 6 SP3 D2 hybrid orbitals overlap with 6 2pz orbital of F. See here, S is present here, all the side. 6 fluorine is present, 2 are axial bond length is present. The 6 SP3 D2 hybrid orbitals overlap with singly occupied 2pz orbitals of F to form stable SF6. Shape regular octahedron. Bond angle is, all the bond angle are equal to 90. That's why all the bonds are equal in length. All the side it is having 90 degree. Next one, SP3 D3 hybridization. Example, formation of IF7 molecule. See here, iodine 53 is the atomic number, ground state. Krypton, after krypton 4s10, 5s2, 5p5. We have to take 5s2 and 5p5. The external valence shell. Excited state, this will jump here. SP3 and 4d3 will form. Overall SP3 and D3 will form. For this, having singly occupied F7 will go and attach there. What will happen, see here? S1, F1, F2, F3, F4, 5, 6 and 7. Overall F7 will form. See all the F in one side 72 degree, another side 180 degree. Overall pentagonal pi pyramidal will form. Bond angles 72 degree in fluorine to fluorine, that is axial bond length, and another side equatorial bond length is, bond angle is 72 degree, axial bond angle is 180 degree, and overall axial and equatorial is 90 degree. All bond length are equal. This is about SP3 D3. Different hybridization schemes involving S, P and D orbitals in simple molecules are indicated in the table below. After seeing all the kinds of hybridization, whether it is SP3, SP2, SP, involving of d orbitals SP3D, SP3D2, SP3D3, these are the kinds of hybridization we have discussed. Based on these kinds of hybridization concepts, we are seeing further examples by seeing in simple molecule. See here, shapes of molecules formed by hybridization involving SP and D. Type of hybridization, orbital atom, dsp2, number of atoms surrounding the central atom, 4, number of bond pairs, 4, shape of molecule, square planar. Example, this is nickel cyanide, that is angle is 90 degree. If it is sp3d, surrounding atom is 5, bond pairs is 5, it will form trigonal bipyramidal. Example, anything you can take, PCl5 also you can take. Angle between equatorial bond 120 and angle between axial equatorial, this is PCl5, that is 90 degree. See here sp3d, D2, sp3 also you can call. Surrounding atom 6, bond pair 6, it will form octahedral structure, here SF6, overall 90 degree. In sp3d3, surrounding atom 7, the bond pair 7, pentagonal bipyramidal, this is IF7, equatorial angle 72, axial angle 90 degree. The overall what we have discussed in the table order we have shown here. To understand, in a short note you can use this table. To understand the hybridization concept you have to go through. Next, shapes of molecules formed by hybridization involving sp-d orbitals containing both bond pair of electrons and lone pair of electrons. Based on bond pair we have seen the previous table, including lone pair we are seeing now sp3d, 4 bonding pair, 1 lone pair, see here trigonal bipyramidal, that will form seesaw shape, okay, that is SF4. SF4 usually by understanding hybridization we will get regular tetrahedral structure, but due to this lone pair it will form seesaw shape. It is an exceptional case. sp3d, 3 bond pair, 2 lone pair, trigonal bipyramidal, but due to this repulsive nature, it will form T shape. Okay, it will pull in this direction. What will form? It will form T shaped, that is CLF3. SP3 D, 5 bond pair, 1 lone pair, it will form octahedral normally. Due to this lone pair, square bipyramidal will form, that is BrF5, that is bromine pentafluorine. SP3 D2, 4 bond pair, 2 lone pair, octahedral it should form, but lone square, due to here one lone pair is present, here one lone pair is present, that's why it will form square planar. This repulsion will take place, it will form square planar XeF4. It is also a exceptional case. We have understood that if the bond pairs only present, the regular geometry will form. If there is a presence of lone pair, it will get an distorted shape. By seeing this table, the distorted shape and with the regular geometry, we can understand. Next one, the coordinate bond. In the previous session only, we have seen that 4 kinds of bond is present, that is ionic, covalent, coordinate and hydrogen. After understanding covalent bond of molecules, geometry, everything, now we are moving to the third type of bond, that is coordinate bond. A bond formed when both the bonding electrons are donated by one of the bonding atoms is called coordinate bond. Both the bonding electrons are donating the electrons. It is called dative bond or coordinate covalent bond. The atom which provides the electron pair for sharing is called donor atom, while the atom which accepts the electron pair is called acceptor atom. The donation of the electron pair is indicated by an arrow drawn from the donor to the acceptor. If something A is donating to B, means the head of the arrow will move towards to B because it's acceptor atom. This is donor atom. Okay, this is dative bond or coordinate bond. Okay, this is the overall concept of coordinate bond. Here, if example, when ammonia molecule and H plus ion approach each other, the N atom of ammonia molecule donates the lone pair of electrons to the electron deficient, that is hydrogen ion, resulting in the formation of coordinate bond. The vacant 1s orbital of hydrogen ion overlaps with SP3 hybrid orbitals of nitrogen atom having lone pair of electrons, resulting in the formation of a coordinate bond. Here in ammonia, this is the structure of ammonia. Here lone pair of electrons is present. In ammonia, we know that. In nitrogen, it will donate towards the 1s of hydrogen which is having deficient, electron deficient is present. What will form? Here, it will donate to here and this is H, it will form a bond. It is donating to hydrogen, so it is a dative bond. This is a coordinate bond. Because this nitrogen is donor, this hydrogen is acceptor. This is having electron rich in nature, this is electron deficient in nature. This is about coordinate bond with an example. And NH3 and BF3 adduct. N atom of ammonia molecule donates a lone pair of electrons present in the non-bonding sp hybrid orbital to the electron deficient, that is B atom of BF3 molecule. This, what it is showing, this nitrogen will donate the electrons to boron. In this case, sp hybrid orbitals of ammonia molecule having a lone pair of electrons overlaps with the empty 2p orbitals of boron. Here in boron, empty is present, it will overlap to here. Thus, a coordinate bond is formed between the N atom of ammonia and B atom of BF3, resulting in the formation of a solid product called as adduct. This is ammonia. Here lone pair of electrons is present. In the boron, empty orbitals are present, p orbitals. What it will form? It will donate to boron empty orbitals. So how it will form? See here, nitrogen to boron. That's why a solid adduct will form, product called adduct. This is about the coordinate bond. In the next class, we will discuss about molecular orbital theory, energy level diagrams of molecular orbital theory and hydrogen bonding. I hope you have understood completely what I have taught today. So we'll meet in the next session. Thank you.